Hi, I'm Willie Harris, and this is the first in a series of 5 lectures I'll be presenting under the topic of phosphorus in agricultural watersheds, science and applications. I'll be presenting Module 2, which focuses on how Florida soils interact with phosphorus. These are the titles for the 5 lectures, and Lecture 1 will be an overview of Florida soils and their distribution. The learning objectives for Lecture 1 include general understanding of Florida soil morphology, big picture understanding of Florida soil types, big picture understanding of Florida soil distribution. I say big picture because I'd like to start with that, and in subsequent lectures we can focus in on a little bit more detail, but it's good to have an overall perspective in the beginning. And I'd like to foster an awareness and appreciation of soil morphology as a means of gathering clues to predict phosphorus dynamics in Florida soils. The lecture outline is: what is soil according to USDA, properties used in describing soil layers, soil horizons, what they are, overview of Florida soil orders, distribution of Florida soils, and some take-home points and references. Soil has been important to humanity probably since the dawn of language and civilization, but it still means different things to different people. For a farmer, it's the medium where crops are grown. For engineers, it's unconsolidated stuff you can push around in construction and that you need to take into account its properties of shrink swell, compressibility, strength, and so forth. We will use the USDA definition for our purposes, and here it is. I'll read it. Soil is a natural body comprised of solids, liquid, and gases that occurs on the land surface, occupies space, and is characterized by one or both of the following: horizons or layers that are distinguishable from the initial material as a result of additions, losses, transfers, and transformations of energy and matter, or the ability to support rooted plants in a natural environment. You have to take a breath after that one. I find that definition pretty cumbersome, so I've given my take on it that I think pretty accurately captures it in simpler language. Soil is material on landscapes, that is on the Earth's surface. We haven't taken it to Mars yet. That either has horizons formed from processes that occurred since deposition or exposure, or has the in-place ability to support rooted plants. Soil scientists consider soils to be a consequence of the classical factors of soil formation: parent material, or the initial material in which the soil forms; climate, which can include microclimate along a slope; organisms, which would also take into account humans; relief or slope topography; and time. There's a set of soil properties conventionally used in describing soil layers. Color is the most evident. It has interpretive significance for soil drainage because it is influenced by organic matter and redox sensitive metals, and wetness in turn affects the distribution of those soil components. Color also has interpretive significance for P retention, and since that's a key issue in this set of talks, then we will go into that more deeply later. Texture or particle size distribution is another important property used in describing soils. It amounts to the proportions of sand, silt, and clay, where sand is 2 to 0.05 millimeters in size, clay is less than 0.002 millimeters, and silt is material that's in a size ranging between sand and clay. To the right, I have depicted a sand-sized particle and a silt-sized particle in proportion to their relative maximum sizes. In this case, at this scale, clay could not even be seen. The term texture applies to mineral components, and sometimes if you have material greater than 2 millimeters, then they are also described, and they would have their own terms like gravel or stones, boulders, and things like that. Texture has a profound effect on soil behavior, and I've given just a few examples of properties that are strongly influenced by texture: infiltration and permeability, surface area and reactivity. Although texture is not the only thing that dictates reactivity, it does have an effect. Moisture retention, certainly, and soil strength, engineering properties of soils, bearing capacity, compressibility, and so forth. Textural classes have been developed based on the percent sand, silt, and clay. The classes are defined by this triangular chart, or the textural triangle, as it's called. If you determine the percent sand, silt, and clay and plot it on this chart, then you will, wherever the point falls, will determine the textural class. We notice that the clay class occupies the biggest part of the chart. That may be because clay has such a profound effect on soil properties, reactivity, and physical behavior, and so forth. So pure clay has a big area, whereas sand and silt have relatively smaller areas on the lower left and lower right, respectively. Classes that fall sort of toward the center, lower center of the chart have the term loam: clay loam, silt loam, and so forth, sandy loam. Loam indicates a mixture of the three classes without one totally dominating. But the terms are pretty intuitive and self-descriptive. For example, when we go from the lower left-hand corner of the triangle, as we move with increasing clay vertically, we go from sand to loamy sand to sandy loam, the sandy clay loam, the sandy clay, and then the clay. So the terms are pretty descriptive of a given material in terms of the texture and how much sand or silt or clay that sample would contain. Of all the soil properties, I think structure, despite its importance, is the hardest to explain. I've defined it here as the way soil particles aggregate into larger units with planes of weakness between them. Individual aggregates are called Peds. I've given some examples of common Ped shapes in Florida soils. Granular or small spheroidal shaped aggregates are common to surface risings, and blocky Peds, which are tend to be a little less spheroidal, a little more blocky in nature, are more common in subsurface loamy and clayey horizons in Florida. Florida soils are not known, though, for having very well-developed structure. I've given some examples of blocky structure from the USDA in the lower left, and a picture of a broken blocky Ped that I took many years ago, failing to use any kind of scale, which is not a good thing when you take pictures. But this was probably about 2 or 3 centimeters in dimensions across the top. This was a ped that it was broken, and you can see that the interior has a gradation in color from red to gray, which relates to the redistribution of iron. And this shows that structure is kind of an architecture in soil. Soils are not isotropic media. Soils are complex biogeochemical systems, and the microbial activity, as influenced by wetness and influenced by the distribution of organic matter, has resulted in the redistribution of iron, its depletion near the exterior of the ped and its concentration near the interior. So soil structure is important not only for the properties that it imparts, but also it's important in understanding the biogeochemistry of soils. Blocky structure can enhance permeability of loamy and clayey textured soils. So in a way it mitigates the effect of particle size. We think of clayey soils as being likely to hold back water, likely to have low permeability, but if you have good structure and you have networks of voids between structural peds, then water can move through pretty readily, even with soils that are finer textured. The voids between peds can transmit water and suspended particles, so they are also a means of, say, clay translocation and clay redistribution. And so often we verify clay redistribution or clay movement in soils by clay being in the form of coatings on ped faces. We don't have to look too far to find an example of how Florida soil morphology is relevant to phosphorus dynamics. People from other parts of the country may think of Florida as a pile of sand, but in truth, soils that fit the textural class of sand can differ markedly in properties. These differences relate in large part to the presence or absence of sand grain coatings, which can retain moisture and phosphorus. Some sandy horizons have coated grains, such as this BW horizon, and some have clean grains, such as this E horizon, depending upon soil genetic processes. And the presence or absence of these grain coatings make a big difference in phosphorus retention, and we will explain a little bit more about the details of that in the next lecture. Mentioning BW and E horizons in the last slide brings us to the topic of soil horizons. Soil horizons amount to inferences we make about soil genesis. I've defined them as layers distinguished by the nature and extent of soil forming processes. This is a very abbreviated summary of master soil horizons. The O horizon is one characterized by relatively high organic matter content. The USDA defines an O horizon as one that has at least 12% organic carbon with no clay and with an 18% organic carbon with 60% clay. O horizons could be things like a leaf litter, or it could be accumulated peat in a very wet area. A horizons are also generally enriched in organic matter content, but less than 12% organic carbon. That is, they don't meet the organic carbon requirement of an O. And they're generally at the surface or below an O horizon, but they can also be used to designate disturbance, such as by plowing or timber harvesting. An E horizon is characterized by loss of fine textured components, and that process is called eluviation. And is characterized by clean sand and light colors, high value and low chroma for those familiar with Munsell color notation. A B horizon can be defined by a number of subsoil processes. So I'm going to emphasize those that you're likely to run across in Florida. A very common one is accumulation of components translocated from above. And another could be in situ accumulation of metal oxides, basically iron and aluminum oxides, or iron and aluminum oxides associated with organic carbon, and other kinds of in situ gains and losses that can occur in the subsurface of the soil. And a sea horizon is one where there is little or no alteration beyond the disintegration of rock, if you have rock present, and rock structure is still evident in more than half the volume, or sedimentary structure could also be evident. And if you reach hard rock, then you would designate that as an R. Subordinate distinctions are used with master horizons. The word subordinate is misleading because these distinctions convey important information about soil genesis and disturbance. They're designated by lowercase letters following the master horizon capital letter. Important ones for Florida, I've listed a few. An AP horizon is one that has been plowed or disturbed at the surface. A BT horizon is one of alluvial accumulation of clay, where the word alluvial refers to accumulation of material translocated from above. And the clay would be silicate clay. Phyllosilicates are what some people call clay minerals. BTG would be an alluvial accumulation of clay plus iron oxide reduction or depletion. BH is alluvial accumulation of aluminum along with carbon and sometimes iron. A BW is an in situ accumulation of weathering products but without appreciable alluviation. And then we have O horizons that are defined by degrees of organic matter decomposition. And OI is fibric organic soil material which is minimally decomposed. OA is sapric organic soil material which is highly decomposed, and OE is humic material which is intermediate between the OI and the OA in degree of decomposition. To bring it all back home with respect to soil horizons, I've combined a picture of a soil profile along with horizon designations and a brief description of a soil that looked very much like the one pictured. So we would have an A horizon that's very dark gray sand with granular structure typically. An E1 horizon that's grayish brown sand and structureless. An E2 horizon, light gray sand texture and structureless. Note that when I have a subdivision of a master horizon, I just use Arabic numerals to make the distinction. In this case, the upper part of the E is a little less light than the lower part of the E, so this is split into an E1 and E2 horizon vertically. Then we have a BH, which is described as a black in color, a sand in texture, and with blocky structure. The BH is an indication of an alluvial accumulation of organic matter and aluminum in Florida generally, with some iron in some cases. And then we have a BTG1, a grayish brown in color, sandy clay loam, blocky structure. And a BTG2, light brownish gray, sandy clay loam, blocky structure. So with a subtle distinction in color, we can subdivide the BTG into a 1 and a 2 vertically. We can make some genetic inferences here because we have the white sand, which would indicate eluviation, a very, very pronounced eluviation, and the BH horizon, which indicates very pronounced illuviation, accumulations from the processes that have taken place in the soil that have depleted the upper part of the soil by the eluvial process, and has resulted in the accumulation of the organic matter along with aluminum, which is given a very dark color to the BH, to the layer that we're going to call the BH. And then we go from a sand texture. We have sand textures all the way through the BH until we get to the BTG1. So we have the T, which indicates that we're inferring that there has been an alluvial accumulation of clay, that is a translocation from above, and that is reflected in the sandy clay loam texture. And we have blocky structure, which can be characteristic of subsurface horizons. And then we have the BTG2, also a sandy clay loam, which is consistent with our interpretation of the T for alluvial accumulation of clay. And in both cases, the G is an indication or an interpretation of there being a depletion of iron as a result of wetness. So the wetness brings about lower oxidation reduction potential and iron mobilization, and either iron depletion or simply iron being reduced and dissolved in soil solution. So the G is an interpretation that we're making that the gray colors are due to the depletion or reduction of iron. I'm going to be using some soil taxonomic terms in future lectures in covering Florida soil phosphorus retention. Therefore, I want to give a brief overview of the most prevalent soil orders of Florida. We'll start with the most common soil order, and that's spodosols, and they're characterized by a well-expressed BH horizon. The second most common soil order in Florida is entosols. They are characterized by having only an A, E, BW, or C horizon within 2 meters. That doesn't mean they can't have other horizons, but within 2 meters, these are the only horizons that would be permitted to classify as an entosol. The number 3 is ultisols, and these are horizons with alluvial layers, BT horizons or BTG, and they have low base status, meaning they have a relatively low proportion of calcium, magnesium, sodium, and potassium in relation to acidity components, hydrogen and aluminum, on the exchange complex of the soil. Number 4 is histosols, which are soils with greater than 12% organic carbon to greater than or equal to 40 centimeters depth. That means you have an O horizon to that depth, and once the O horizon is that thick, it becomes an organic soil or a histosol. There are abundant histosols in the Everglades and some other areas of Florida as well, but mainly in the Everglades. Number 5 is alpha sols. These are soils that are basically indistinguishable from ultisols in terms of morphology, but they also have a BT or BTG, but they have higher base status. They have a base saturation, which is the percent of the sum of bases, potassium, magnesium, calcium, and sodium, divided by the total cation exchange capacity times 100, and that is less than or equal to equal to or greater than 35% for alpha soils, as distinguished from ultrasols, which have a base saturation at a prescribed depth of less than 35%. And then we have mollisols. Some people don't think of Florida as a place where mollisols would occur, but they do occur here, generally in wet environments, and they're characterized by thick, dark A horizons with high base status, again, high base saturation, high proportion of bases relative to acidity components throughout the profile. And they can also have BTG horizons, but as of the one pictured here, but they're not required to have that. They're only required to have the thick, dark surface horizon and the high base status. This is a general map of the soil orders of Florida created by Dr. Vic Carlisle, who was a professor in the Soil and Water Science Department, University of Florida. The distribution of orders is closely tied to physiography. The most extensively occurring landform of Florida is flatwoods. And spodosols are prevalent soils on flatwoods, and therefore they're the most extensively occurring of the 8 soil orders of Florida. Entosols are second in extent. Most entosols occur on highly weathered geomorphic surfaces. In effect, even though they classify as entosols, they're not young and unweathered, except where they're forming in recent sand dunes, floodplains, and such landforms. There are also entosols in South Florida dominated by carbonates on younger surfaces. The carbonates could be relatively well-drained rock-plowed soils or very poorly drained soils that have formed in accumulated secondary calcium carbonate. A term used for that material is marl. Some take-home points for this lecture. Florida soils form in diverse parent materials, including sands, loams, mucks, and carbonates. Mucks and carbonates are most common in the area south of Lake Okeechobee. Soil forming processes can be inferred from soil morphology, and we'll have more examples of that in subsequent lectures. Soil morphology provides information about composition and behavior, including phosphorus retention, and we'll certainly expand upon that in subsequent lectures. Sandy horizons can differ markedly in properties, such as moisture and phosphorus retention, based on presence or absence of grain coatings. And Florida soil distributions relate coarsely to regional physiographic patterns.